Are you ready, Professor?
Oh my god, it's still not letting me record.
Well, I just
So,
started recording on my machine, so if you want to,
oh, perfect.
I
Okay,
can just send
as
you the
long as we.
recording when we're done.
Okay, thank you. I appreciate that. Please continue.
You're welcome. Okay, so the first thing I'm going to do is I'm going to show you the starting point for bitvm, or at least for me it was, which is logic gates. So I'm going to open up a little program on my computer here called Logisim, which is a circuit board emulator. Have you ever seen Logisim before, Professor?
I, interestingly, I have, but not in the context of Bitcoin.
Mm-hmm. Yeah, well, let me show
What?
you just
Yeah,
briefly,
yeah.
for the
Please.
sake of the video, so other people can see the starting point, how this thing
Yeah.
works. So I'm going to put two logic gates out here. A circuit board simulator is, well, circuit boards are like what computer chips are made of. And the first thing I'm going to do here is I'm going to show you how to make a very basic program that does addition. So I'm going to do that using two things called logic gates and a couple of things called pins. And let me just connect a pin here and connect a pin to this one. And I will extend these wires out so we can see the results, because the results will appear on these wires. And then, so what this gate right here does is called an AND gate. And when you put two pins on it, like I've done here, if you turn one of the pins on, the AND gate will not let the electricity, represented by this green wire here, flow through to this output wire unless both gates are on, right? So this is called an AND gate. This gate needs to be on, or this wire needs to be on, and this wire needs to be on in order for electricity to flow. If either one is off, or if both are off, the electricity will not flow. That's an AND gate. The one down here, let me draw another wire. The one down here is called an OR gate, or XOR rather, exclusive OR gate. And the difference between this one, let me just show you from the perspective of both of them being off. For an exclusive OR gate, if both of the wires are off, then no electricity is going to flow through here. If one of them is off and the other one is on, then it will, because either this one has to be on or this one has to be on, but not both. So if I flip this one off and turn this one on, electricity will be flowing through this one. If I turn both of them on, well, it no longer meets the condition. It's supposed to be either one can be on but not both. Well, here both are on, so electricity is not flowing. Well, what we've done here, by combining these two logic gates with AND and an XOR, we've created a little binary counter. This thing can actually count how many wires are connected to electricity right now. So if you look at the outputs and you treat those as binary output, this is going to be one number, this is going to be another. If I just turn one on, one electricity, one of these wires, then the output reads as 0, 1, which in binary is the number 1. If I just turn the other one on, it's 0, 1 again. And if I turn both of them on, well, now it's 1, 0, which in binary is the number 2. So it actually, this by just combining two little logic gates like this, which you can do on a little computer, on a little circuit board, you can see that that we've got a little counter here. It's actually adding two numbers together. So this is the starting point for bitvm, is that we figured out a way to make a circuit board like this that can run in Bitcoin. And the reason that's cool is because every computer, like every computer that exists, is created by just using logic gates on circuit boards. So we can simulate an entire computer on Bitcoin by making a really big one of these, a really big circuit board with lots and lots of logic gates on it, and running it on Bitcoin. So I'm just going to zoom out here, and I'm actually going to recreate, to show you how we do this, I want to recreate this in Python, because there's a Python program I have that lets me output something that I can use in bitvm. So are you ready to move to the next phase, or do you have any questions at this point, Professor?
Hold on, super. So a NAND gate is what's called a universal gate,
Mm-hmm.
which means any function can be written in NAND gates.
Yep. This is
So
what a NAND gate looks
effectively,
like.
right. So effectively, you're saying if I gave you an input-output relationship, some functional relationship, vector in, vector out, you can represent them in terms of logic gates,
Mm-hmm.
and or not, or NAND gates, etc. And because you can, you're able to run a input-output relationship with logic gates, right? That's what you're saying.
Correct.
Did I get that right?
Yeah,
Okay.
in
Now
any
let me take
program.
it one.
You can represent any
So
program this way.
awesome. Now that is great from an ALU perspective, which means essentially you're able to replicate within a processor and ALU, but there is still memory and buffers, and
Mm-hmm.
you're saying you're able to handle those as well, right? So if you just took a basic microprocessor, it has a couple of components beyond just the logic, right?
Yep.
Um, registers. How
Registers
are you
and
able to
clock.
Yeah, exactly.
Yeah, so I will show you how we do memory registers. I've actually built a computer in here that does that, but I do there is like a bit of a procedure. So if you can hold on to that question, and I will come to it
Sounds
when
good.
I show you the full computer I built, because I can show you then
Nice.
how I do memory registers. So the next thing I'm going to
Excellent.
do, I'm going to pull up Sublime Text Editor, and I don't need this one or this one. Those are other projects I'm working on. I'm going to show you how to represent this logic circuit in Python, and then how to go from Python into something called a Bristol fashion logic circuit, and from there into Bitcoin. So to do that, I need to open up. I need to import some libraries, and I forget where they are, but I can find them using Firefox because I've stored some of my code for this on my GitHub. So if I go to the Tapleaf Circuits repository on my GitHub, I have some stuff here that I can show you. Or actually not this one. I wanted to do the 8-bit CPU for bitvm because the little Python file right here has what I need for it. So let me pull this up and get these libraries. I'm going to put them into Python. And I don't need this one, and I don't need you. And is there anything else? I don't need him. Okay. So I've got a couple of libraries here. One of them is the circuit library, which is for emulating logical circuits. This is called a Bristol fashion circuit library. This creates an intermediate representation that we use to import stuff into Bitcoin. And then, well, the other one's the system, which I don't actually need system either, so I'll get rid of that. So the first thing we're going to do is we're going to create an input wire. So I'm going to call it gate 0, and I'm going to do c dot, let me go get the syntax for this, c dot gate input. Okay, I'm going to create a logic gate whose kind is identity. And we're going to use this logic gate as an input. So we can set an identity gate to either 1 or 0 and specify that this is an input to our circuit. And this will be used to represent these pins that are on this page. It'll be, this is going to be this pin. We also need to represent the other one, so I'm going to create another one called gate 1. That'll be that. The next thing I need to do is represent these two logic gates right here. So I'm going to have gate 2 will be an AND gate, and it will take as inputs gate 0 and gate 1. It will not be an input gate. And so that's what that one does. I think that's all it needs to do. Op.and, let me just make sure. Yeah, you just specify what gates it takes as input. And then we need an XOR gate. So I'm going to do gate 3 will be an XOR gate. And it will also take gate 0 and gate 1 as inputs. And then lastly, we need to represent these two output wires right here. And the circuit library wants us to represent those separately. So we got to make 2 more identity gates. And these ones are going to be is output equals true. And we will actually specify here which ones they represent. So they represent G3 or G2 and G3. We'll take the outputs of gates 2 and gate 3 and turn them into identity gates where we specify that these are outputs. So now I can actually run this program, and we can put inputs into it and see the results. So let me go down and get the syntax for that. It's print.evaluate. And if I do an evaluation of a 0 and a 0 as our inputs, then what we should see here, if I save this as, let me do it as testing Python circuit.py. I'm going to open up.
So by the way, Super, here you're just testing the Python program. It's nothing to do with Bitcoin yet.
Not yet. We haven't done anything with Bitcoin yet. We're getting there.
Yeah.
But I'm going to
Just making
run
sure.
with Python. Actually, I have to Python 3. What was that called? Testing Python circuit.py. Oh, I have to. I have to put this in a directory that has those those modules installed. So let me move this. Move testing Python circuit.py into a folder I created called PyCircuit, and then this is one that I've been experimenting and making all these different programs in. So when I'm in here, I can do Python and do testing Python circuit.py. And when I do that, I put a 0, 0 in as input, and I got a 0, 0 in as output. And that's exactly what we'd expect. If I have 0, 0 on these pins, the outputs are 0, 0. If I change to
just real quick, Super, the G0 you may want to rename.
how come?
Towards the end. Maybe G4.
Oh, yeah.
Last two.
4 and 5. You're right. Yeah. Okay. So if I put a 0, 1 in here, we should get a 0, 1 as output because one wire is connected. If I change that to 1, 0, 1, 0, we should still see 0, 1 because only one wire is connected. Yep, that's what we got. And then if I turn both wires on, both inputs, we're going to get a 1, 0 because that's binary for 2. So I've recreated this entire logic circuit in Python. And now that it's in Python, there's one other thing I can do, which is I can use the Bristol Fashion Circuit Library to export this in a way that I've written a program that can import it into Bitcoin, which I will show you. But let me just grab these two lines and get rid of this guy because we're not going to need to evaluate it anymore. But instead, we will, for every line, we're going to go through and use the Bristol Fashion Circuit Library to print an equivalent circuit diagram. So let's just show you what this looks like. So what I've created here is a circuit diagram that is written in this Bristol fashion. And this tells you, it's kind of obtuse how it's written here, but it tells you there are four lines in the program. So that's what the first, let me zoom in so you can see it. The first line up here tells you that there are 4 lines in the program. It tells you how many wires are involved. So if we look at this, we've got wire 1 and wire 2. Those are our identity gates. They go into these things. So if we count them, there's 1 wire going in there, a second wire going in here, third and fourth. And then lastly, there are 2 output wires. There's a total of 6 wires involved in this circuit. So that's what that second thing is telling you up there. It tells you that there's one set of inputs, and the inputs are a total of 2 bits. So that's these guys right here. Those are 2 bits of input. And then as output, there's one set of outputs, and the output indicator is 2 bits. So that's going to be these 2 wires right here are our outputs from our program. So that's what those are telling you. And then each line down here tells you how the logic gates are hooked together. So this tells you that the AND gate takes 2 wires as input, and it produces 1 wire as output. The wires we're hooking into it are 0 and 1, and we're setting output wire 2 to be the result of ANDing 0 and 1 together. Then the same thing down here, an XOR gate takes 2 wires as input, 1 wire as output. It's taking 0 and 1, wire 0 and wire 1 as inputs, and then it's setting the result to to wire 3. And then our output wires just take 2 and 3, 2 and 3 down there as input, and they only have 1 output, and they just set wires 4 and 5 to be equal to those. So our outputs end up on wires 4 and 5. So this this little thing right here, this format for representing circuit diagrams, is called Bristol fashion. It's just a format for representing this kind of stuff in a way that a computer can understand. And so I wrote a little program. This is the whole idea for bitvm is based on the idea that you can take logic gates and you can represent them in Bitcoin script. So I wrote a GitHub repository called Tapleaf Circuits, which takes a Bristol circuit as input. You pass it a Bristol circuit. You can actually see some of the ones I've run in here in the circuits library. All these things, like this is an 8-bit adder I wrote as a Bristol fashion circuit, and down here is like a bit shifter, because we were building a SHA-256 function. We need stuff like bit shifting and in addition and stuff like that. But we've written a bunch of programs as Bristol circuits, Bristol fashion, logic circuits. And then I made this little program, I think it's in vm.js, which is able to take one of these circuits, one of these Bristol fashion logic circuits that look like this, as input and produce a corresponding Bitcoin address that encodes all of that, that encodes every line of code here as a tap leaf. So at this part, we're getting into the part where we're getting into Bitcoin, and I need to explain what tap leaves are. And to do that, I'm going to pull up a what's it called? A slideshow that I presented at TabConf, or not TabConf, at a couple of different Bitcoin conferences. And there's a slide in here that tells you what tap leaves are. So let me wait till it loads and then go down to that. So in here, I was just showing people how logic gates work, and then I was showing them how Bitcoin transactions work. And here is where I told how tap leaves work. So let me make this full screen so you can see. Here I have a representation of Taproot. So Taproot was a upgrade to Bitcoin that went live in 2021, and it made it possible to create a Bitcoin address that has many different scripts inside of it. One Bitcoin address with many different scripts. So Bitcoin has the ability to run small programs which we call scripts, as part of the mechanism for unlocking a Bitcoin and spending it. And usually the script is very simple. It just says, like, if you are able to prove that you know the private key to this Bitcoin address, then you're allowed to spend the money. That's like a standard script that we use in Bitcoin. But we actually have support for a lot of functions in script that allow you to make more complicated programs. And Taproot allowed us to combine many of them into a tree structure, where every script that you have as an option for spending your money is given a little number, or it's given a little identifier rather. And when you go to spend your money, you specify by means of the identifier which script you're going to use in spending that money. So for example, maybe number 14 over here might be a standard, if I can prove that I have the private key using a signature, then I can spend the money from this address. That might be the script we have in number 14 over here. And so if I wanted to spend the money using that, I would have to say, all right, I'm going to use script number 14, prove that that's part of this address, and then I can provide my signature and spend the money. But for over here, maybe this script is different. Maybe for this Bitcoin address, script number 13 might say something like, if you can find the two numbers that add to the number 5, then you're allowed to spend this money. Like that would be very insecure, because anyone can easily find two numbers that add to 5. But you could do that. You could make a script that says, instead of providing a signature and a public key and a private key or whatever, you just have to find two numbers that add to something else, and then you can spend the money with that. And for every script that's in here, they all get a little identifier, and you get to specify as the spender which one you're going to use to spend your money. And that's what Taproot enabled. So what we'd use is we create a little tree structure using every line of code from one of these Bristol circuits. We create a tap leaf in Bitcoin script that commits to one of these logic gates. And we can do that because Bitcoin script has support for all of the logic gates. If you look up all of the functions that are available in Bitcoin script for constructing programs, we've got opt-not, where's not? Right here, opt-not. It allows you to put in a 1 or a 0, and it will reverse it. It will flip it from a 0 to a 1 or a 1 to a 0. That's called the inverse gate. We've got something called op bool and, which is right here. And this allows you to take a 0. You can pass, it does what the AND gate does. If you put two zeros in, or a 0, 1, or a 1, 0, the output will be 0. And then if you put in two 1s, the output will be 1. We've also got Boolean OR in here, so we've got Boolean AND, Boolean OR. The versions of XOR is actually the same thing as num not equal. That's what Bitcoin calls XOR, and then XNOR is called num equal in Bitcoin. But we have support for all of the logic gates because you can combine AND, OR, NOT, and XOR and XNOR to get all of the logic gates and then do anything you want. Any one of these you can actually turn into a Bitcoin script. So that's what tap-leaf circuits does. But the other thing that needs to happen in order for bitvm to work, in order to simulate this, is we need a way to actually commit to what inputs we're putting into this program. Here in this example, I'm putting in 0, 0, but we might want to put in 0, 1, or 1, 0, or 1, 1, and we need a way to have somebody do that. We need a way for them to commit to saying, I'm going to put a 0 and a 1 into this program. Now, normally in Bitcoin, when you create a transaction, you have something called the witness script. And in the witness script, let me zoom in on this thing. In the witness script, you specify the inputs to your program. Oops, didn't want to do that. So if you were going to use a 0, 1, the witness script is typically an array, just like this. And if you were going to use a 0 and a 1, you might put, op 0, and here I have op 10, but that's for something else. You might put op 0, and then you might put op 1, and actually, here's a better example. There's op 0. You might say, I want to put the number 0 and the number 1 next, and that would be my inputs to the program. However, that's actually not secure. It's not secure to do that in Bitcoin because your signature in Bitcoin doesn't commit to the contents of the witness script, of the witness stack. Of the elements that you put as inputs to your program are not committed to by your signature. And that means they're changeable. They're actually malleable. This was something that we introduced with SegWit to make it so that we could do the Lightning Network. It needs stuff to be malleable, or it actually fixes malleability. But because of some changes we made in SegWit, it is not safe to actually just put raw numbers on your witness stack, because then people can change them and ruin your program and make it, you put a 0 and a 1 on here, but then they switch it to a 1, 0, and now instead of getting well, in this case it would be fine, but if they could change it to a 1, 1 and then make it say that the output is 1 or is 2 instead of being 1. So that would be bad if they can just change what's on your witness stack. So what we do is, and this is where tap-leaf circuits comes in, we use hash commitments. We use, I wish that when I clicked on something in GitHub, it wouldn't pop up a little thing here to tell me about that little thing. I don't want it to do that, but it keeps on doing it. We use hash commitments. So we actually, if I come down here to challenge address, which is where we're actually using this thing, generate challenge address. Insert, not that one. Yeah, this one. So what we do is, stop doing that. We use hash commitments. So for every time you want to represent a 0 or a 1, we create a little, we create a, something called a promise file, which I will show you a promise file. So I will go into downloads, I think is where I have some, and open up this promise file. So this is me running an 8-bit computer in here. And for every input, like in my 8-bit computer, I needed to put some 1s and 0s as input. And for every one of those, we create a hash. So this is a long stream. Let me go. This is called initial commitment hashes. This is an array of a whole bunch of hashes where each one is going to have a pair of hashes, one that represents 0 and one that represents 1. And so for every logic gate that's in this little thing right here, of which there happen to be 2, we would create 2 hashes for every bit of input, a hash that represents 0 and a hash that represents 1. And we would commit to a program in Bitcoin where it does what this thing shows. We're going to, the person who is going to spend the money is going to reveal the preimage to one of those hashes. And if he reveals, this one, this is the hash representing 0 for the first input bit, and this one represents 1. So what we do is we hash the preimage that he reveals, and we compare it to the hash representing 0. And if it equals 0, if it equals that hash, then we say, okay, they're the same, and we drop a 0 on the stack. We insert input 1's value here. So that would be this one. This is input 1, and if it's a 0, he's going to reveal the preimage to this hash, and so we will drop a 0 on the stack right where it says insert the input 1's value here. Otherwise, if it doesn't match, then we're going to drop. Then we're going to check if it equals this one. We're going to say, does it equal? Does the preimage he revealed equal this one? And if it does, then we're going to drop a 1 right there on the stack where it says insert input 1's value here. So by using hashes and preimages, we are able to allow someone to commit to a value in a way that nobody else can modify. No one else can no one knows what preimage he has that equals this hash for the person who's running this program. So they can't modify it on the witness stack and then cause the program to run incorrectly. The program will just say, hey, if it wasn't the preimage to either of these, then it's a failed transaction and the transaction won't go through. But the person who's running the program, he is able to reveal inputs to these logic gates because he does know the preimages to these things. And so he can say, yeah, I'm going to reveal, for this one, I'm going to reveal the preimage corresponding to 0. And then for this one, I'm going to reveal the preimage corresponding to 1. And the hashes and preimages trick allows us to ensure that nobody can change them. The other thing we do for bitvm is, each of these wires is going to have a hash pair. So this one, let's call this one AB. I wonder if I can draw with this. Are you able to draw in Zoom? I don't think so. But I can use a label. So let me use a label on here. So we would put AB is going to be the name of the hash that Paul is going to reveal for this part that's going into this wire. And then let's just put down here that this one is going to be C and D. So for this program, he would have to reveal A and B right here. He would have to reveal either A or B, one of those preimages, to represent a 0 or a 1 here. And he would have to reveal a C or a D down here. And then down here, we would put E and F, and down here would be G and H. I think A, B, C, D. Oh, yeah, E and F, G and H. So then the output wires, he also has to reveal those. He has to say what the output of his program is going to be. So over here, we would have, if we have A, B, C, D, E, F, and G, H, then this is going to be I and J are going to be the wires over here. So that's going to be for this set of logic gates here. He would have A. He would reveal A or B. He would reveal C or D, and then he would reveal I or J as the output for this logic gate. So if we wanted to connect two logic gates together, like let's say this program had another AND gate over here, and this guy went into that, and this guy went into that, and then this was our output wire. All we do in order to connect two logic gates together is we reuse these hashes and preimages. So IJ is going to be both the output for this gate and the input for this gate. So somewhere in here in this promise file, if we have two logic gates that are hooked up together, there's going to be two hashes that are identical. There's going to be a hash pair that's going to be used for this one as well. And so when Paul wants to commit to his program, up front he has to send Vicky, he has to send the person who's verifying his program all of these hashes for every single logic gate and for every single input so that they can construct the program that they've agreed to run and ensure that their tap leaves have all of this information in it. That for every tap leaf on here, let me go back to this thing to show you the tap leaves. So that for every one of these, they've got, for number 14, for number 14, which is going to be on here, the last logic gate is an AND gate with IJ as input and whatever two hashes are going to be down here. Their number 14 script in Bitcoin is going to say Paul has to reveal either hash I or hash J, and then one of the other two hashes for the other input. And he has to reveal both of those. He has to run it through an AND gate. So we're going to drop a 0 or a 1 on the stack for each input, and then we're going to run those through an AND gate. And then Paul has to reveal the output, which is going to be one final, let's just say it's, like Y and Z are the two last, Y and Z are the two last things he has to reveal. He has to reveal one of these that is like true. If he puts a 0 and a 1 into here, and then we run and then we're going to run the AND thing on them, this has to come out as a 0. So he has to reveal a 0 right here. And what the tap leaf circuits thing does is if he reveals the wrong thing, if he says 0 and a 1 come out as a 1, when you run him through an AND gate, we just make it so that the person verifying the program can take his money. She can just run off with his money because he lied. He said that 0 and a 1 produce a 1, and they actually produce a 0. So we just encode that as, Vicky can. We call them Paul and Vicky. Paul is running the program. Vicky is verifying that he did it correctly. Vicky can take his money. And but as long as he doesn't lie, as long as he runs the program correctly, and every single tap leaf accurately, he says what hashes go into it, he says what hashes come out of it, and he never lies, then Vicky never has a chance to steal his money. Like the program always comes out true, and he never lies. So that's what we do for bitvm. We send each other these things called promise files that have hashes for every input to the circuit. And and let me just show you the coolest thing that we've got running with this thing is this 8-bit computer. And so here's the computer in there.
On this 8-bit computer, let me ask you a quick question.
Yeah.
Don't you need a compiler from Python to essentially to Bitcoin opcodes? How are you compiling from a Python program to a opcodes?
So the question is, how are we compiling from the Python program to opcodes? Well, we use this intermediate representation right here, the one called a Bristol fashion circuit, and this breaks it.
Can you take an arbitrary Python program and then reduce it to this intermediate step?
Well, as long as it's using this, this circuit library to recreate a logic circuit.
So it has to be in logic circuit libraries. I see.
This with my implementation, it does. Yeah.
I see. So if there was a way to take a high language program, reduce it to logic circuits first, then use these steps. So maybe sort of the compiler has 3 steps. Step 1, take the high level program, break it down to ALU circuits. Step 2, take those ALU circuits, break them down to this intermediate language. Step 3, take that,
which is this one.
into opcodes.
Yep, that's exactly what my tap leaf circuits library does. It takes this intermediate representation, or the Bristol fashion library, and it converts it into opcodes, and makes a Bitcoin address that has a tap leaf for every line of code on here, along with hashes and pre-images that reveal whether you're inserting a 0 or a 1 into it. And using that,
yeah, totally. I totally,
you get the rest.
Totally
well, I understand that you get it, but for this, since I might be showing this thing on YouTube.
Let me shut up. Yeah, please do.
I do want to show, because we're almost done. We're almost done here. I created this big logic circuit down here, which represents a computer. So this down here is called an ALU, which is the arithmetic and logic unit. And it has all of these hashes and pre-images and stuff that go in and out of it. I've got memory registers, which are represented by all of these things. These are 16 different bytes of RAM. And for every one, you have to use logic gates. This is called a selector, to select a byte of RAM that you want to write to or read from. And then we've got something over here called a bus, which takes the whatever byte of RAM that you've said, and it puts it up here on the bus, which is these wires up here. And once something is on the bus, you can move it using logic gates. Again, you can move it to a new register, or you can move it to the ALU or whatever you want. And this very complicated circuit down here, with all these different parts, constructs an 8-bit computer with 16 bytes of memory, and it runs. This whole thing runs and produces this thing. It produces this little representation. So if I open this and view the circuit. Let me go down to what's it called? I think it's var circuit. Yeah, this circuit is in the intermediate representation. It's got over 1,000 different lines of over 1,500 lines of code in it, over 1,800 wires involved, and it takes 128 bits of RAM as input, along with a bunch of other stuff for other things, and it produces this huge, long, program here. But this runs. I wrote a little thing that can run it, and I even implemented a programming language called assembly. So this, you can actually write programs in assembly. So here I've made a little counting program. You can actually see
Very cool.
you put the instructions for the program into RAM, and if I'm going to toggle this into decimal so you can actually see. Right now it's going to run a no op, which is where the computer does nothing. But if I start incrementing the clock here, it'll say like this is an assembly function called load immediate, which loads a value into the A register, and it's going to load 0 into there because we're initializing the counting program to 0. And if I just keep incrementing the clock for a few times, it gets down into the next instruction, which is add, and it's going to add the contents of the 15th byte of RAM. So if we count the RAM, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is number 15. We're going to add this number, which is 3, to the A register, which was initialized to 0. So we should see the A register turn into a 3 in a second. So, yep, there it did. It turned into a 3. And then we keep incrementing the clock, and the next instruction says to store the value of A in byte 14. So after a few seconds, we should see a 3 show up right there. And yep, there it is. And if we keep incrementing the clock, then it jumps back to the previous instruction and runs it again. So now this is a 6 because we added 3 again, and we store 6 down here, and then we just do that again. And if we auto increment the clock, you'll see that all it does is, this is the output register down here, output 14. It's just counting up by 3. And so, yeah, this is Turing complete. It even has jump. Like, you can jump back to a previous instruction. Because, and this actually runs on Bitcoin. You can run this little computer and write a program in assembly, and you're limited, in this case, to 16 bytes of RAM. But, you can do anything you want with it. I made a little bounded loop program where it breaks out of the loop after a certain amount of time. So if we incremented this, you would see that it starts counting up from 252, and then once it hits, I think it's going to hit 255 and overflow. So right here it just hit 255, then it's going to overflow, and now it's going to break out of the loop and store and not be in it anymore. It actually halts the computer. But this is a Turing complete computer that runs on Bitcoin, and it's constructed using these tap leaves things. So we've moved on from this. We actually have a 32-bit CPU that runs now, and instead of having 16 bytes of RAM, it has 16 gigabytes of RAM. And so that's what we're working on now. We're adding assembly instructions to it. But yeah, this VM lets you run pretty much anything.
Can you make the assembly x86 compatible?
Yeah, we can find the circuit for a x86 computer.
Actually,
and then
better. Can you make? You know what? We can make this RISC compatible.
Yep, that is
Instead of CISC, because if you make it RISC compatible, I mean, again, RISC or CISC, either one will work, but the RISC set is a more minimal set. Let's do this.
We're doing
Let's
RISC-V.
wait.
We're doing a RISC-V
RISC-V,
CPU.
You're going RISC-V?
Yeah, we're making a RISC-V CPU, and the programs for it are all in this bitvm GitHub project.
Nice.
But we actually have a working 32-bit RISC-V CPU. Well, it's not. No, that's not true. We have a working 32-bit CPU. It doesn't have the full instruction set architecture for RISC-V yet. We're currently adding that, and we expect to have it done by the end of this month. So.
Nice.
Yeah.
By the way, so let me. Can I know I've been peppering you with tweets. I apologize, but let me ask maybe one or two things, and so number one, the computer you're developed is running offline, right? You're only putting a proof of it at the end on base chain, right? You're not, in fact, everything else you're
Yeah.
running off chain.
So what happens is Paul and Vicky, we call them, they agree on a program that they want to run. They fund a Bitcoin address that has, all of these tap leaves created, and there are like millions of them for all of these logic gates. And then they don't actually, once they have money in the program, Paul's committed. Like he has to reveal outputs that produce, or he has to reveal inputs to the program that produce an expected output. And if he lies or if he does the computation incorrectly, Vicky gets to take his money. So all of that stuff actually happens off chain. He actually reveals the information that's supposed to result in the program off chain. That's supposed to result in the expected computation off chain, and she just validates it. She puts the inputs he revealed into the same program, into this thing, for example, and if it comes out the same for her, if she says, yeah, he put in these inputs and it produced the same output, and she says, all right, I'm not able to prove that he lied. I'm not able to prove that he contradicted himself. So they just move forward. She sends him, he gets a reward because a time lock will either expire on the Bitcoin address, and then he'll be able to take the money in it, or she'll just send it to him, and then they'll not have a dispute. But if he sends her inputs that produce a wrong result, she can actually show which line of code it breaks. And she can show, like, at this point, he says it comes in as a 0 and a 1, but it comes out as, yeah. So she does that, and then the script lets her take his money. So only if there's a dispute does anything go on chain. And what we did there, we used something called binary search to make it so that even if you have a very long program, she can check only 32 steps of the program, 32 points along the of each line of code, because you can think of this as an ordered list. This is line 0 of the code. This is line 1. This is line 2. This is line 3. If she checks the middle one, right here, and she says, okay, I put in my copy of the program says that there's supposed to be a 0 and a 1 here, and it comes out as with XOR that would come out as a 1. She checks to see if he has the same thing, and if he has the same thing there, then she knows the error comes later in the program. So this is called binary search, where you cut off half the program every time, and it allows us in only 32 steps to have up to 2 to the 32 lines of code, and that's what we want for RISC-V. In order to do a RISC-V computer, obviously it's a very long program, but with only 32 on-chain transactions, she can always find where the disagreement happened and prove that Paul lied and ran the computation wrong. So we use binary search for that in order to make it so that you have a very minimal amount of stuff that goes on chain, and each of these scripts that goes on chain, if you look at it, it's longer than a normal Bitcoin script, but it's not that long. It's like probably 50 bytes in this thing. So that's like less than an inscription or an ordinal. Even a BRC20 token has more than 50 bytes of data in it. So these are they're relatively big, but not that big transactions. And with only 32 of them, we can run an entire RISC-V computer, which is really cool.
Very cool. So let me do this. I want to digest this. Do you have time? Because a couple of things. It turns out that zero knowledge proofs are also just logical circuits. In the end, everything is a logic circuit, right?
If it runs on a computer, it's got to be running on one of these things eventually.
Exactly. They're all finite state machines with logic. So I can walk you through some of those aspects. But also, if you're reducing to RISC-V, for RISC-V, zero knowledge proofs already exist. And what's more, with the RISC-V architecture, there's a lot of languages you can compile down to that might work. So we can also think through, it doesn't have to be RISC-V, but we can think through the RISC-V ecosystem a little more carefully here as well. And then finally, I think there could be a way, and I do want to understand the other token classes you mentioned, especially you mentioned BSC, right?
BRC
to
20 tokens?
understand BRC20 tokens you mentioned.
I did. I mentioned them as an example of something that takes up more space than a bitvm transaction.
I understand, but I do want to understand that too because it might be synergistic here, and I might be wrong there. But so, would it be okay for me to think through this and then get back with both of you? Maybe I mean I'm sure you'll be busy end of the week, but maybe after that, or maybe as soon as Thursday.
If
Yeah,
you,
I am very available to meet with you guys any day.